About 300 years ago, a French scientist named Blaise Pascal discovered that leverage can be applied through a confined fluid. Pascal noted that a small force on a small input piston becomes a much larger force when the resulting pressure is applied to a larger piston. He stated this fundamental principle of the hydraulic lever as Pascal's law. Pascal's law says pressure on a confined fluid is transmitted undiminished in all directions and acts with equal force on equal areas.
Now, hold it just a second. How about putting that into American so the master technicians and I can apply it to servicing brakes, power steering, and automatic transmission?
That's just what I'm going to do, Tech, if you'll be patient. When you're putting up a building, you have to put in a foundation first, you know. And Pascal's law is the foundation of pressure hydraulics. Having gotten it out in the open now, we can put our story together piece by piece. The science of hydraulics covers a pretty wide area. In the broad sense, hydraulics can be defined as the science of liquids in action. You master technicians get involved in two branches of hydraulics. One that uses the impact energy of fluid in motion, and one that uses pressure to transmit force. A water wheel or turbine is the simplest example of using impact energy. The wheel is put in motion by moving fluid striking against blades or vanes. This principle is used in torque converters and, of course, in harnessing electricity from a waterfall. In pressure hydraulics, the motion of the fluid is incidental. The work is done by applying pressure, that is, by pushing on a confined fluid. Today we're going to stick to pressure hydraulics. Now, to show that pressure hydraulics isn't really difficult, let's build a simple system and see how it works. First, we need a storehouse for fluid until it's needed in the system. We call this storehouse the reservoir or sump. Next, we need a pump to take the fluid from the reservoir and push it out into the system. In other words, the pump causes flow. Valving is used to regulate pressure and to control the amount and direction of flow. Then we have a working or actuating mechanism to change pressure energy to mechanical work. Here's the complete system then. Fluid under pressure comes from the pump through pressure lines and pushes the actuating mechanism so work is done. Besides the pressure lines, there are often return lines to release fluid back to sump when no work is being done. Hydraulic brakes are a familiar example of a complete system. The sump is part of the master cylinder. The master cylinder piston doubles as a pump piston and a valve. The working mechanisms are the brake cylinders. Now that we've seen what goes on in a pressure hydraulic system, let's take a closer look at this thing called pressure. First, though, maybe we'd better explain the difference between pressure and force. Force is simply a push or pull exerted on an object. One kind of force you're all familiar with is the force of gravity, which is actually an object's weight. In hydraulics, we're often concerned with another force, spring force. For example, in applying a hydraulic servo or shifting a spring-loaded valve. Regardless of what kind of force you're talking about, the unit of measure is the same, pounds. Pressure is force divided by area. For example, if a uniform weight of 1,000 pounds rests on a surface 100 square inches in area, the force on each square inch is 1,000 divided by 100, or 10 pounds. We then say that the pressure on the surface is 10 pounds per square inch. The unit for measuring pressure is pounds per square inch. It's abbreviated PSI. Pressure is created by applying force to a confined fluid. If the fluid isn't confined, it will just flow when force is applied. But when there is a resistance to flow, pressure results. Pascal found that when force is applied to a piston in a cylinder, the pressure in the fluid trapped below the piston equals the force divided by the piston area. If the force is 100 pounds and the piston area is 10 square inches, the pressure is 100 divided by 10, or 10 psi. This pressure is present everywhere in the trapped fluid. And regardless of the shape of the container, every square inch of container area is subject to the same 10 pounds. The pressure is transmitted undiminished and acts with equal force on equal areas. This also means the total force on any area equals the pressure multiplied by the area. For instance, if we apply this 10 psi pressure to a larger piston, say with an area of 100 square inches, the total force is 10 psi times 100 square inches, or 1,000 pounds. And so we have 100 pounds input on the small piston balancing 1,000 pounds output on the large piston. This effect is called force multiplication, which you may know under a different name, mechanical advantage. Here it's gained hydraulically instead of mechanically, but the effect is the same. Here are a couple of examples of hydraulic force multiplication. In a hydraulic brake system, the input force is applied to the relatively small area of the master cylinder piston. The output comes through 8 wheel cylinder pistons which have a much larger combined area, so total force at the brake shoes is greater than at the master cylinder. Another example is the kick-down band in a torque flight. When it's applied by a pressure of 95 psi on the servo piston area of about 4½ square inches, the servo force is over 400 pounds. When you multiply force like this, you don't get something for nothing. Remember the rule, energy can neither be created nor destroyed. When the output force is greater than the input, the output travel must be less.
Sounds like robbing Peter to pay Paul, but I suppose it's okay if Paul needs it and Peter doesn't.
That's just how it is, Tech. To illustrate this, suppose you're using a lever to raise 1,000 pounds with a 100-pound input. You can do it easily enough, but the lever has to be 10 times as long on the input side, and it has to travel 10 times as far as the output. The same is true in our hydraulic system. When the output piston is 10 times the area of the input piston must travel 10 inches to displace enough fluid to move the larger output piston 1 inch. Now let's take this little system and make it into a simple hydraulic jack circuit. To do this, we must add an oil reservoir and suitable valving to permit repeated stroking of the input piston or pump. 2 check valves are needed, one to keep the load from coming down on the intake stroke and one to prevent pressure loss on the power stroke. On the intake stroke, the small piston moves up, creating a void below it. The reservoir check valve opens and permits fluid from the reservoir to flow in. The load tries to lower, but this creates a pressure that seats the load check valve and traps the fluid. Then, when the input piston starts down, it creates pressure in the fluid below it and seats the reservoir check valve. The load check valve opens and permits the fluid to flow under the large piston, raising the load another notch. To lower the load, we add a needle valve between the large piston and reservoir. Opening this valve lets the load push the fluid back to sump. What about the matter of flow now? As you can see, the output of this system is both force and motion. Therefore, the system uses pressure and continuous flow. Pressure to apply the force and flow to create motion. In other systems, such as brakes, the output is primarily force. Thus, there is only enough flow to actuate the working mechanism and maintain pressure. So far, we've only looked at piston-type pumps that use a strong right arm or foot for a power source. Most systems are powered by rotating engines or motors and use rotary pumps for smooth, continuous output. So let's spend a few minutes now seeing how rotary pumps work.
Before you do that, someone better take the needle pressure off that side of the record and apply it to the other side.
Most rotary pumps used in pressure systems have two round members of different size. The members are on different centers, so at one point there's no clearance between them, and the clearance varies through a half revolution to the point of maximum clearance. The pumping mechanisms, slippers, vanes, lobes, or gears, form sealed chambers between the members, and these chambers are carried around by rotation of one or both of the members. As the chamber passes the pump inlet, it's increasing in size, creating a void. Atmospheric pressure in the sump forces fluid into this void. Rotation past the inlet traps the fluid in the pumping chamber. This is how we get pump displacement. Further rotation causes the chamber size to decrease. Fluid is squeezed out into the system as the chamber passes the outlet. By having successive chambers follow each other closely, a smooth, continuous output is maintained. Also, the continuous chambers seal the outlet from the inlet, so pump delivery is positive even against high pressure.
That's why you have to have a relief valve with this kind of pump.
That's right, Tech. When there's no room for flow into the system, pressure could build up until something gives. The relief valve meters the fluid back to sump and maintains system pressure. But that's getting away from our story. In the slipper pump, used in power steering, the inner member is a rotor, which carries 4 spring-loaded slippers. As the slippers follow the surface of the stationary outer member, or cam ring, they move in and out of the notches in the rotor. The pumping chambers are formed between succeeding slippers. The slippers seal against the cam ring, so fluid at the outlet is sealed positively from the inlet. In the lobed rotor-type pump used in torque flight, both members turn. The inner rotor is driven and carries the outer rotor around by meshing of the lobes. A pumping chamber is formed between 4 lobes. The chamber size increases as the lobes are separating from mesh at the inlet. The chamber decreases as the lobes mesh again at the outlet. The inlet is sealed from the outlet by the close clearance between lobe tips. Well, that's a quick sketch of pumps. So let's talk about valves now. The orifice is actually the simplest means of controlling flow and pressure. An orifice is a metering opening. It slows down the flow of fluid either to create a back pressure or to delay buildup of pressure downstream. When fluid is pumped through an orifice, it is restricted and a back pressure is created. In some cases, such as the flow control valve in a power steering pump, this is the reason for an orifice, to create a difference in pressure between 2 chambers that fluid is flowing through. If the fluid becomes blocked off beyond the orifice and flow stops through the orifice, pressure soon equalizes. In the torque flight transmission, orifices are used to delay the application of pressure to make shifting smooth. Another very simple type of valve is the check valve. A check valve is a one-way valve. It permits flow in one direction and blocks it in the other direction. A ball check valve consists of a steel ball and a seat. When pressure is applied on the seat side, the ball moves off the seat to permit flow. Pressure on the opposite side holds the ball against the seat and blocks flow. The poppet-type check valve has a flat disc that seals around a hole smaller than the disc. A light spring holds the disc seated and guides it back into position after it has been unseated by pressure. A simple relief valve is similar to a check valve. It usually consists of a ball or cone-shaped poppet and a heavy spring that holds the valve seated against pressure. A relief valve has an adjusting screw to vary spring tension and thereby vary the pressure at which the valve opens. Another common type of hydraulic valve is the spool valve. It's cylindrically shaped with 2 or more lands and with annular grooves between the lands. It's closely fitted to a round bore and slides back and forth in the bore on a pressurized film of fluid.
Yeah, if it isn't all varnished up. If the wrong fluid is used, or if the fluid gets too hot, varnish is formed. Varnish will coat the valve bore so the valve sticks. That's one reason it's darned important to use the right amount of Mopar or Cryco fluid, and to change the fluid periodically in severe operation.
Right again, Tech, but you're getting away from our story again.
Guilty as charged, Your Honor, but I had to get that point in. I'll shut up now while you finish.
Spool valves have to be handled carefully because it's so easy to raise burrs on the sharp edges of the lands, and the edges must not be rounded off, or dirt will get under the land, which can make the valve stick or scratch out a leakage path. In fact, dirt is the big bugaboo for all valves. If dirt gets under a check valve, it won't seal tightly and control can be lost.
Who's straying now?
Touché, Tech. But back to the story. Ports in the system are blocked by the spool valve lands or interconnected by the annular grooves between lands. Spool valves are positioned manually or by pressure. Some valves are forced in one direction by a spring and shifted against the spring by applied pressure. Sometimes two or more pressures are working on different areas of the same valve, and there's a spring thrown in too. Remember that any pressure can be resolved into force by multiplying pressure and area, and the valve will move away from the greatest total force. There are two basic types of spool valves: regulator valves and relay or directional valves. A regulator valve controls pressure and flow, and a relay valve directs pressure and flow. A relay or directional valve could be compared to a traffic cop or a light switch. It simply tells the fluid when and where to go by interconnecting or blocking passages. It doesn't in any way restrict flow. A regulator valve is like a variable orifice. It's used to regulate pressure or flow rate and operates by metering fluid. By metering, we simply mean that it passes a restricted flow. Here's how a regulator valve works to maintain a constant pressure. The valve has 3 port connections, from the pump to the system and to sump. A reaction area opposite the valve spring is connected to the system port, so system pressure reacts against or opposes the valve spring. Before fluid begins to flow, there's no reaction pressure. The spring positions the valve so the sump port is covered. All the pump delivery is to the system until pressure builds up. As pressure increases in the system, it reacts against spring force. The valve moves and begins to uncover the sump port and let part of the pump delivery go back to sump. If the pressure tends to decrease, the spring forces the valve back to block pump delivery from sump. The valve land and sump port become a variable orifice that automatically adjusts to meter fluid, to sump and maintain pressure. The back pressure on the pump side of the orifice is the system pressure, and it's determined by the spring force. Auxiliary pressures can be introduced to change the system pressure. For instance, operating a torque flight transmission in reverse, a pressure source is connected so it assists the spring and the regulated pressure increases. Just a word on sealing pressure now before we wind up. Sealing applications can be classified as static or dynamic. In a static application, the parts being sealed don't move in relation to each other. In dynamic applications, there is rotating or reciprocating motion between the parts. O-rings are used effectively where motion is limited to seal closely fitted parts. They seal in both directions and take up little space. When the mating parts are assembled together, the O-ring is squeezed at the inside and outside diameters. Pressure on either side of the O-ring forces it against the side of its groove, providing a positive seal on 3 sides. The lip-type seal is also a positive seal and can be used to seal high pressure in dynamic applications. The seal lip is installed toward the pressure source, and pressure against the lip balloons it out and aids sealing. Metal seals are not positive. They are used to seal rotating shafts that carry fluid under pressure and need some leakage to lubricate the shaft journals. Metal seal rings are also used where high temperatures are encountered. Well, that seems to have run us out of time for today.
Yes, but we haven't run out of material. There's a lot more in this MTSC reference book, including a section on atmospheric pressure, vacuum, and gauges. So I hope you master technicians will study up on hydraulics during this month so you'll be all ready for next month's session where we'll apply the principles we've learned today.